Hi, so my name is Kateryna Andrych. I'm a final year PhD student at Macquarie University, supervised by Devika Kamas and working with quite a broad international team of collaborations as well. So it's an honor for me today to present this talk and to give a review of structure of disks around evolved binary systems that I'm working with in my PhD. So let's start with some planets. Traditionally, planets, including those in our solar system, are discovered orbiting young stars. So most exoplanets identified so far are thought to have formed during the early stages of their host star life. This happens as residual gas and dust from the star formation condense into a disk and provide material for planet formation. Here is, for example, on the slide, protoplanetary disk around T Tauri type star, imaged with near-infrared high-resolution imaging, and there are two currently confirmed planets in the system. You can even see one of them on the image over here. And here is the HR diagram, which maps the luminosity and temperature of stars that host confirmed exoplanets. It reveals that the majority of host stars fall alone or just after the main sequence. However, there are exceptions, such as exoplanets found in more evolved systems, like those orbiting white dwarfs, for example. Moreover, back in 1992, the first two exoplanets were found orbiting a pulsar, which is a vastly different astrophysical site than was expected. This system has now 3 confirmed exoplanets, and while it isn't likely that these planets survived the supernova explosion, they seem to be formed from gas ejected in this explosion, which settled into a disk or a ring around the pulsar and gave rise to a new generation of planets. So what this tells us is that exoplanets can form pretty much in different environments, and the key ingredient to form planets is the disk of some sort around the star or a binary system. Of course, this is getting more complicated because disks itself are not homogeneous. And here is, for example, a snapshot of protoplanetary disks around young stellar objects, result with near-infrared high-angular resolution imaging. As you can see, protoplanetary disks are common in all sorts and flavors, and they do show various morphology with arcs, spirals, gaps, rings, and so on. So this complicates understanding of planet formation because we need to first understand disks and their diverse structure. Recently, research led by Hans van Winkel, Devika Kamas, and a broad team of international collaboration has shown that there is another phase of stellar evolution where a disk can be formed. So if we look on the binary system on the right side of the slide, while one of the companions in the binary evolves through the asymptotic giant phase, it loses the majority of its envelopes through mass loss driven by stellar winds. In case of a binary system, the gravitational influence of the companion can strip away the material from its outer layers, terminating the evolution of the asymptotic giant branch. This mass transfer process, induced by binary interaction, can lead to a formation of a stable dusty disk, not just around the secondary companion, but around the binary system itself. And this is what we called a post-asymptotic giant branch binary system or post-AGB binary system. And as I mentioned earlier, the presence of disk is crucial for planet formation, and therefore we need to investigate the properties of this disk and compare them to protoplanetary disks in order to understand if disks around evolved binary systems can be potential site of planet formation or not really. So now, to make my talk a little bit interactive, I hope it will work. Yes. Yes. So can I please kindly ask you to pick up your phones and scan the QR code on the slide? And then on your phone, you'll see the question, how probable do you think it is for new planets to form around evolved binary stars with disks? And there are 3 options. So please choose one of them, and we'll see results in real life. And I will ask you the same question in the very end of my talk, so we'll see whether your decision or your answers will change or not. Let's give it a little bit more time. Okay, 16 people, 17. Okay, look like it stopped. We do see pretty nice distribution, honestly. Yeah, nice. Okay, so let's move on and we'll do the same question in the very end to see whether we've changed the distribution or not really. All right. So I'm not going to talk in detail about single stars, and please come tomorrow for the talk of Hans van Winkel and also Magna Menon and Maxime Moran for more details on the single star and more details on post-AGBs in general. However, I want to note some of the main properties of the single post-AGB star. So this is a low to intermediate mass star in fast transition between the asymptotic giant branch and planetary nebula phases. Post-AGB stars also have a low surface gravity and metallicity, as well as significant near-infrared excess in the spectral energy distribution. So this excess is attributed to the presence of dust around the star due to the stellar winds, both for single and for binary system as well. As I explained before, in case of binary system, the AGB phase of the primary star is terminated by the binary interaction, and it's resulting in the formation of various structures, including a stable circumbinary disk. So here is, for example, a sketch of the typical post-AGB system. So we have a post-AGB star, main sequence companion, circumbinary disk around the binary system. We also do have a small circumcompanion disk around the main sequence star, and we have a bipolar jets that bipolar outflows, we also refer to them as jets, launch from the position of the secondary companion. If we compare the system to representation of the protoplanetary disk around the young star on the right side over here, this representation is taken from Delmont and Monnier paper in 2010, you can see that systems do look very similar. Even though the luminosity of post-AGB star is much higher than luminosity of young star object, and that's why the disk is starting further away in terms of a distance from the central binary. Moreover, the initial post-AGB system structure was adapted from passively irradiated protoplanetary disk model developed for young stellar objects. And it was shown that this model works pretty well to reproduce interferometric observations for post-AGB circumbinary disks. Our research group at Macquarie University, led by Devika Kamas and a broad collaboration, used various observational techniques in order to comprehensively study these complex systems. So each observational data gives us information only about the particular part of the post-AGB system, and we do need to incorporate them all together to get a full view on the system. While binary post-AGB stars were detected serendipitously, they show characteristic spectral energy distribution, or ACD, wherein the dust excess peaks in the near-infrared. So here on the image, you can see the characteristic spectral energy distribution for the post-AGB binary system. And on the x-axis here, we have the wavelengths, and on the y-axis, we do have the corresponding flux. As you can see, towards the lower wavelengths, the spectral energy distribution of the post-AGB system differs more and more from the modeled single star ACD. And such near-infrared excess is commonly attributed to presence of a stable circumbinary disk for young star objects, for example. We also know that because of the shape and location of this near-infrared excess, the dust inner rim of the disk is supposed to be somewhere near the dust sublimation radius. High-resolution radial velocity monitoring of several post-AGB stars has shown variable absorption features that were interpreted as jets. When the evolved companion in the system appears behind the secondary star, continuum photons from the primary star get absorbed by hydrogen atoms in the jet, resulting in, resulting in variable shape of H-alpha line profile. So in the image here, you can see the dynamic spectra of H-alpha line for the post-AGB system. The velocities on the x-axis denotes the radial velocity shift from the systematic binary velocity, and the y-axis represents the orbital phase. Recent studies of H-alpha line time series demonstrated that the jets in post-AGB binary system are generally wide and have outflow velocities of the order of hundreds of kilometers per second. It was also shown that post-AGB binary jets are comparable with outflows for young stellar objects in terms of size as well as the speed. Spectroscopic observations allowed us to determine the binary orbital parameters, presence of crystallization in the disk, as well as amorphous and crystalline silicates. We also can see that for post-AGB binary system, we have a chemical depletion of refractory elements or elements with a higher condensation temperature in the post-AGB photosphere. I'm not going to talk a lot about spectroscopic details, so if you're interested in this particular part of the post-AGB systems, please come tomorrow to talks of Magda Menon and Maxime Macquarie. But I just want to highlight the depletion pattern of refractory elements that we see here is very similar to what we see in young star objects as well. So one of the common explanations of this effect is the ongoing reaccretion of the material from the circumbinary disk back on the post-AGB primary star. And the reaccretion happens only for the cleaned gas, not the dust in the disk. So more elements with a high condensation temperature got stuck in the disk. They're not reaccreted back. That's why we have a domination of volatile or elements with a lower condensation temperature in the stellar photosphere. Now, coming to the disk, finally, deep near-infrared interferometric studies specially resolved the hot dust inner rim of the post-AGB circumbinary disk, confirming that the inner rim is located predominantly at dust sublimation radius. However, the recent study has shown that similar to protoplanetary disk, we can separate the group of transition disk targets within the post-AGB disk sample, where the dust inner rim is located not on the dust sublimation radius, where it should be by theoretical predictions, but much further away. And when I say much further, it can be up to 7 times larger. So we do have a large inner cavity for a subgroup of disks. And for protoplanetary disks, the same kind of size and the same cavities are usually interpreted as the presence of giant planet carving a hole in the disk. While we don't know yet what is the mechanism of this large cavity for post-AGB binaries, it is very interesting that we do have the subset of such disks for evolved targets as well as for young targets. And coming to radio interferometric observations, they show us the dust emission and as well as gas emission further away from the central binary. So we see the more extended disk structure. And these studies have revealed that post-AGB circumbinary disks exhibit Keplerian and sub-Keplerian rotation. They also have a typical angular size around 1 arc second. And moreover, radio interferometric observations allowed to directly measure the gas mass of the disk of around 10 to the power minus 2 of the solar mass. Advanced direct imaging instruments equipped with extreme adaptive optics provide access to light that is scattered from the small dust grains on the disk surface. And these observations allow us to directly resolve the extended disk emission and the structure of the disk itself. However, due to typically large distances to post-AGB binary systems, around 1 kiloparsec and more, we cannot use chronographic masks to block light from the central star because the post-AGB primary itself is too bright to simultaneously just resolve the disk and the binary system in the center. So we do need to somehow block light from the central binary. We cannot use chronographic mask, it's too large, and therefore we rely on polarimetry to separate light from the central star and light scattered on the disk surface. Stellar light is mostly unpolarized, but after scattering on the dust grains on the disk surface, it became polarized. So we can use polarization as a method to differentiate between light scattered on the disk surface and light just directly emitted from the star. In addition, using the polarimetric approach, we can extract information about dust properties encoded in the intensity, distribution, and also wavelength dependence of the polarized emission of scattered light. So on this slide, there is, for example, the high-resolution image of post-AGB binary system IR puppies. And for this system, the disk is nearly edge-on. So this is a dust emit plane of the disk, and it partially blocks light from the central star. So we can resolve the disk itself even without using the polarimetry. However, if you have a pole-on disk, when you see simultaneously the disk and the binary, you cannot do this, and you do need polarimetry. So this is what my research is mostly focusing on. I use observation of the sphere instrument mounted on one of the ESO-built telescopes. And this instrument has two cameras, which allows to perform high-resolution imaging and polarimetric observation in both optical and near-infrared wavelengths. So now coming to high-resolution imaging of post-AGB circumbinary disk with sphere. Our study capitalizes on observations from both cameras. So we have observations in 3 bands, in optical, V and I band, and in near-infrared H band as well. Our target sample consists of 11 representative systems that cover a wide range of stellar temperature, orbital inclination and period, also chemical composition and spectral energy distribution. I also like to note that in our sample, we have both a full disk system, when the dust in a rim starts on the dust sublimation radius. Yeah. And we also have transition disk systems where the dust starts further away and we don't yet fully understand what is the mechanism behind it. While we're not yet sure what causes this large inner cavity, it is interesting that transition disk systems are found to be even more similar to protoplanetary disks around young stellar objects and hold potential signatures of possible second-generation planet formation. Yeah, so here are already reduced linearly polarized intensity images for all 8 post-AGB objects observed in the near-infrared V sphere. These are already images where we corrected for the light from the central star, so you don't see the central star here. And because quite often we can't resolve not just the star, but the part of the disk itself, when we are correcting for the light from the star, we kind of always subtracting it. So this dark innermost part on nearly every image, it's not the inner rim of the disk, it's more observational bias effect because we can't resolve the inner rim of the disk yet. However, as you see here, we found a range of different substructures and different orientation and sizes of the disk. In terms of substructures, we found that some systems have outflows, additional rings, arcs, and also scattering on the opposite disk side. So, as I've already mentioned before, we do have full disks and transition disks in our sample. And we found that 2 systems classified as transition disk do not show a clear elliptical shape surface of the disk as the full disk system do. So this further supports the suggestion that these targets are intrinsically different. We also find that some systems exhibit bright substructures, while others lack extended polarimetric emission. Our findings indicate a correlation between the presence of these extended substructures in polarimetric images and the proxy of initial metallicity of the post-AGB star. Although many factors can influence this effect, it is possible that disk morphologies are related to the initial metallicity, potentially due to the lower dust production during the AGB phase of the primary star. We were also able to perform the direct measurement of the post-AGB disk scale height or the disk thickness in the extended parts for two systems. For the left system on the slide, we estimated the height above the midplane of the outer disk based on the visible shift of the outer ring in this image from the position of the central binary, that is a projectional effect. So while we do know the inclination to the system, we can estimate what height above the midplane for this ring should cause this observational shift. And for the system on the right, we actually resolve the disk dusty dark midplane. So this is a scattering on one side of the disk, and this is a backward scattering from the other side. So we can directly measure the thickness of the disk by measuring this shadow in the middle. This parameter, the scale height of the disk, is one of the crucial parameters for the radiative transfer modeling and also for further interpretation of observations, not just from high-resolution imaging, but others like interferometry. Coming to multi-wavelengths approach, as you can see from these images, results from both optical and near-infrared align pretty well, confirming previously defined disk orientation and also showing various structures. We do need to combine different wavelengths of the polarimetry in order to define the wavelength dependence of polarimetric brightness of the disk, the color of the disk, and then connect it to the dust grain parameters predicted by the physical dust models. Because with just single wavelengths, we can only estimate and establish the structure of the disk, but we cannot talk at all about dust grains, which we can with multi-wavelengths approach. So let's focus on one of the targets, RS08, which is quite extensively studied previously with interferometry and has polarimetric imaging observations in all three bands. We have optical and near-infrared bands here. Resolved disk surface for the system shows more elliptical shape with shorter wavelengths. So the left image on this slide shows the polarimetric direct imaging in the V band, so it's around 5,500 centimeters. And the right image shows the polarimetric imaging in near-infrared H band, so it's around 1,600 nanometers. So interferometric studies showed that the inner rim of this particular disk is definitely ruled by the dust sublimation temperature. So we can expect it to be mostly circular and interpret the changes in the shape as projection effect caused by disk inclination. Therefore, here we obtain higher inclination for the innermost disk part towards the lower wavelengths. Moreover, the disk polarized intensity relative to the stellar flux is higher for shorter wavelengths. So we cannot say that we don't resolve the more extended disk part here because we didn't have enough exposure. No, we did. So the difference in the extension of the disk and also difference in observational inclination should be caused by something else. Both difference in inclination and extension of resolved disk structure combined with a known fact that the dust opacity decreases with the wavelengths led to the idea that disk might be warped. So recent observations of young stellar objects show that warped disk surface is really quite common for protoplanetary disk. So therefore, we can assume that it can be one more similarity between post-AGB disk and protoplanetary disk as well. So we do assume that disks, and we have some observational results here that show that there is potential warping in post-AGB binary disks as well. We also have investigated the brightness distribution along the disk surface and found that on shorter wavelengths, disk appears to be brighter on the northern side. I'm not sure whether it's seen here, but it's brighter over here than on this side, and it's quite clear in V and I band, so in optical wavelengths, and the effect is less towards the near-infrared H band. This disk asymmetry is a clear sign of more effective forward light scattering on the dust grains in the disk. While for small particles, scattering is isotropic, in case of relatively large particles comparable with the wavelength size, scattering is more efficient for the smaller scattering angles. Therefore, presence of bright forward scattering peak at these wavelengths is consistent with the porous dust aggregates of around 1 micrometer size. And this suggests also that the northern part of the disk is closer to the observer, so the disk oriented something like this donut. Polarized brightness of the system was measured relative to the total unpolarized intensity of the binary, so we can directly compare the system with the protoplanetary disks around Tauri and Herbig stars. So here on the left side, you see on the x-axis the wavelengths, and on the y-axis the polarimetric brightness of different disks. The blue one on top is our post-AGB circumbinary disks, and others are different protoplanetary disks around young star object. As you can see, our system is among the brightest in terms of polarimetry. And on the right side of this slide, I have also shown the color index calculated for different protoplanetary disks and for our post-AGB system as well. So when the color index is less than minus 0.5, the disk is assumed to be polarimetrically blue. When it's between minus 0.5 and 0.5, it's gray. And when it's larger than 0.5, it's red. So for our system, we found the polarimetric color of circumbinary disk be grayish, which is quite typical for protoplanetary disks as well, and is consistent with dust aggregates instead of single monomers producing this scattering and polarization. Now on this slide, you can see how high angular resolution imaging results complement existing near-infrared intrametric data. So on the left side here, there is a combined polarimetric image of IRIS-08 circumbinary disk in optical and near-infrared direct polarimetric imaging. And on the right side, there is an intrametric reconstruction of the dust inner rim of the disk. And now here is a table of different properties of protoplanetary disks and post-AGB disk. And as you can see here, despite the different formation nature, slightly different mass, and definitely different disk lifetime, they do share a lot in common. And we do have a lot of similarities between post-AGB circumbinary disks and protoplanetary disks around young stellar objects. So let me now ask you to once again pick up your phones and scan the QR code and answer the same question. How probable do you now think it is for new planets to form around evolved binary stars with disks? Okay, it doesn't look right now like I convinced somebody. But it's only 9 people yet, so let's wait a bit more. It was around 27 people answered the last time. Is it updating? Should be. Well, all right then. We do have just 9 answers. Maybe it will update a little bit later. But yeah, anyway, From these 9 answers, it doesn't look like I convinced you that there is possibility of the planet formation around evolved binary system, but we are looking very curious on this possibility and working to find the exact answer on this question. So here is my conclusion slide. And I would like to note that right now, combining all the observational data, we are finally come to piece together this very complex system. And we're looking forward to more results, but in our opinion, they do look very, very similar to protoplanetary disks. And if it's not possible for them to form large planets, it might be possible for them to form some planetesimals, or at least quite big rocks. And in addition, studying these disks around evolved binaries is very important to study the disk binary interaction processes that are not fully understood yet as well. And going forward, we are keen not just to extend the sample of our data and observe more post-AGB disks, we also looking forward to use some of the already existing instruments for our targets, like Subaru telescope instruments, some of the new coming upgrades for the sphere, and also upcoming instruments like MAVIS and ELT. And with this, thank you very much for your attention, and I'm happy to answer some questions.
Thank you, Kateryna. Do we have questions?
Hi, Katya, that was a fantastic talk. So my question is that, do you observe disks of varying metallicity? Do you find that low metallicity disks are less likely to form planets?
I wouldn't say that we have answer whether they are more likely or less likely to form planets. The only link so far to the metallicity or the correlations that we found, we can estimate the initial metallicity using this proxy, zinc over age, because the iron big elements are highly depleted for post-AGB primary stars, so we cannot use it as a tracer of initial metallicity. We can use zinc. So with this tracer, we do see that for elements with lower proxy of initial metallicity, the size of the scattered disks, the size of extended emission is lower. But that's so far the only thing that we can say connected to metallicity, and we have to work more on this correlation as well.
Thank you very much for the presentation. It was very instructive. So I have a question regarding, you were pointing to the fact that usually, I mean, there is this tendency to link the cavities to the formation of planets in Protot. But on protoplanetary disks, we also know that these cavities can be formed by photoevaporation, for example. And I can imagine that in the case of post-AGB stars, surface temperatures are similar, but luminosities are orders of magnitude higher. So I can imagine that the photoevaporation in this case could be even more important than in protoplanetary disks and be the cause behind this cavity. So can you exclude that from what you are doing?
Well, yes, we do take it into account. And if we come back to the models, I'm not sure whether I can click as fast, but yeah, anyway. So we do take into account when we do a model of circumbinary disk, we take into account the different luminosity. But in terms of photoevaporation, yeah, it might play a more significant effect, but we tested and we don't think that it would be so significant to be responsible for like up to 7 times larger dust in the rim of the disk, like located much further away than it should be. Like it's not so significant to explain this effect. So we're still looking for the potential mechanism that can be responsible for that. We're currently hoping for planets, but maybe it's something else.
Okay, thank you very much.
Okay, other questions?
Can you say something about what the evidence is that the binary companion is actually a star as opposed to a substellar object?
We do have a radial velocity monitoring, so we do have estimation for the companion mass, and we do know that the distribution of the companion masses corresponding to main sequence companion, not something smaller and not a white dwarf. So these post-AGB binaries, we have a post-AGB primary and we have a main sequence companion.
Thank you.
Hello, it was a nice talk, thank you. It's a bit a more general question about post-AGB disks, and I think the answer is not known, but so we don't know how these disks form. But if I'm right, they have to be present at the end of the AGB phase, because in the post-AGB phase, there's no way that there's that much mass that can still accumulate.
Yeah, of course. So, well, we do know how it's formed. We don't yet have the full model that can go from the AGB field to the stable post-AGB disk, circumbinary disk. But the idea is that during the AGB phase of the primary star, it loses a lot of mass through the stellar wind. And in case of presence of the companion, this mass goes like even faster stripped away by the binary interaction. And instead of just forming the envelope and going for the depletion nebula stage, it forms a disk. At least some part of the mass that is injected during the AGB phase forms a stable circumbinary disk around the system. So this is the source where the mass is coming to, and we do have an estimation of dust mass of the disk, at least for one system. It's around 10 to the power minus 3 of solar mass. And in terms of gas, we have estimation and measurement from the radiative interferometry, and it's around 10 to the power minus 2 of the solar masses. Yeah.
Yes, because I saw that you put that numbers indeed. So then I was thinking, like, if we have the massless rates of 10 to the minus 7 or something, then like at which age of the AGB should they start forming that we can still have that much mass in the disk? Because I was like,
yeah, so in this case, the AGB evolution gets terminated because the companion strips away the envelope of the AGB star, and it kind of stops the AGB evolution. And we come to like a little bit earlier, stopping the AGB phase and going to post-AGB for primary companion and all this mess around them.
do we have an estimate of like which percentage of the envelope would end up in the disk? I'm not sure how.
We have estimations from, let me say, from radiative interferometry. We do have some measurements for gas, because we have not just the disk. For some targets, we also trace more extended structure of the outflows, driven by the stellar winds during the AGB phase. And onto the disk, the settling is around 50% and less of the ejected mass.
That's quite a lot, but yeah, that's interesting. Thank you.
Very nice talk. I have a curiosity about the whether it was very nice, this comparison you made between the protoplanetary disks around young stars and these post-AGB stars. Are there some cases where it is not easy to differentiate whether the disk is around a young star or a post-AGB star, or there is some clear diagnostic?
No, it's quite clear, because the luminosity and the chemical composition, the spectra of post-AGB star is significantly different from the young stellar objects. So there is a clear, and for protoplanetary disks, for young star objects, the disk is much larger in general, and the spectra of the star is different, luminosity of the star is different. For post-AGB, we straight away see it from the spectral energy distribution, we see it from spectra, it is definitely a post-AGB star, and then it gets trickier to actually resolve the disk, because targets usually much further away. So there is no risk for us misinterpret whether we are looking at protoplanetary or post-AGB circumbinary disk. But yeah, we do build a lot of links, because disks looks so much similar to protoplanetary disk. So this is the idea that despite the different age and different stages, we can have again a disk around the star, and potentially we can have the same processes as happening for young stars.
Okay, thanks.